This video covers the last step of building the regression model. We have looked at the data. Based on what we saw, we estimated a linear model. We estimated the parameters for that model. We evaluated both the parameters and the quality of the fit, whether or not that linear model was the correct one to use. So we're satisfied with the model that we have. Now it's time to put it to use. There are three things that we're going to do under step 5. First, we're going to develop a confidence interval for the slope, or beta 1. What this confidence interval is going to tell us, remember the slope is the relationship between x and y. In terms of the data set that we're dealing with, it's the price per square foot. We've got a point estimate for that. We need to know how high that point estimate or how low that we have a point estimate for the slope. We need to know how high or how low the true value might actually be. Second thing that we're going to take a look at is for some value of x, where might we expect to find the model? Where might we expect to find the expected value of price? The third thing is predicting an observation. Again, given some value of x, how high, how low is it likely we're going to see a single value? And the difference is the difference between a mean and an individual observation. If you remember confidence intervals, values of x, values of x bar. So the confidence interval for the slope, we're going to use a formula that's very similar to formulas that we've used for all confidence intervals. We've got a point estimate, we have a critical value of t, and we have a standard error of the point estimate. We put these together, critical value of t times the standard error. I'm going to refer to that as a margin of error. And the confidence interval is simply going to be B1 plus or minus that margin of error. I simply put the margin of error together as a matter of convenience. Limits the number of calculations we have to do. Interpretation of this confidence interval, it is a range that we expect to include the true value of the slope. In other words, the true price per square foot for a house. What's going to affect the confidence interval or the estimate? Well, the confidence level. If we have a small value of alpha, our confidence interval is going to be pretty wide. If we are willing to take a small value of alpha, say a 90% confidence interval, our range is going to be fairly small. Second thing that will affect the confidence interval is the size of the sample. Sample size increases, critical value of t is going to go down. The estimate for the standard error is going to go down as well because we've got more information. Where do we find this critical value of t? We go to any t table. I pulled one off of Google. Your management science text has one. You can even use Excel functions. So, let's develop a confidence interval for the slope. Point estimate for the slope is 0.0479. Critical value of t. If we go to a t table and we look for a two-tailed test, alpha of 0.05 and 11 degrees of freedom, this is the error degrees of freedom, n minus k plus 1. The critical value of t that we're going to need to use is 2.2. And the standard error of the estimate. If we go to our parameter estimates table, we're going to find the point estimate and the standard error of that point estimate for square feet. Put this all together, we end up with 0.0479 plus or minus 0.0127. Lower confidence limit 0.0351, upper confidence limit 0.0606. Graphically, 0.0479 is in the middle, 0.0606 is the upper limit, and 0.0351. Now, just an interesting piece of information to tie this together with our hypothesis test back in step 4. If the confidence interval contained 0, we would not have rejected the null hypothesis, because if this range contains 0, that means 0 is a possible value for the true relationship. And if 0 is a possible value for the true relationship, we're not going to have sufficient evidence to reject the null hypothesis. The next two things we're going to take a look at are estimation and prediction. Estimation and prediction are a little bit more complicated because we need to know how far we are from the center of mass. And the reason for that is this uncertainty in the slope. Center mass is the center of the data set. And if we have estimated a slope of 0.0479, but if the true slope happened to be 0.0606, that would be our line. And if the true slope happened to be the 0.037, I believe, that we found, that would be our true line. Notice that as we're close to center mass, it really doesn't make a difference what the slope is. But the further we get out, the more that uncertainty is going to affect our estimate of where the true model is. Now, where is the true model? It's going to be somewhere in this inner confidence interval. What does this confidence interval mean? Well, suppose we are looking at a house that's 1,500 square feet. Expected value of that house is going to be about $75,000. But if the slope is a little higher, it's going to be $80,000. If the slope is a little bit lower, it's going to be, say $70,000. So depending on what that slope is affects the range we might expect to see the true price. For individual observations, notice that this interval does not contain all the points in the sample, and it's not likely going to contain all the points in the population either. At that house, 1,500 square feet, this is the range that we expect the true model to be. But second interval, the prediction interval, shows us where we might expect to find individual observations. Again, it's going to be influenced by how far away we are, but the effect is a little bit less, or less significant. The difference being those lines are more less like an hourglass. Now, how do we find the distance, or how do we quantify that distance? We do that using a distance value. And the distance value formula looks pretty ugly, but it really only has three components that we need to worry about. 1 over n. Larger the sample, the smaller that part is going to be. We've got a sample of size 13, so we're looking at 1 over 13. The numerator of the second part, x sub p minus x bar. If we're predicting at 1,500, x sub p is 1,500, x bar is center mass, we're taking this distance and squaring it. The denominator, SSXX, represents the total variability in the x-axis. And it is from x bar measuring each distance and squaring it. Now, of course, you don't want to do this to find SSXX. And this may look a little bit familiar if you think about how we find variance. For variance, we're taking x sub I minus x bar. We're squaring that, and we're adding them all together. That is SSXX. To get variance, we divide this by n minus 1. So if we have the variance of x, and we multiply that by n minus 1, we get SSXX. Where do we find the variance? Well, we find the variance the same place we find the mean. We're going to need to take a look at the distribution of x. And I've gone ahead and pulled a distribution of x. Key things that we're looking for: the mean, x bar is 1203, and the variance of x is 138 933. And if we multiply that by n minus 1, we get the total variability, SSXX. And that is going to be 1,667,204. So we need to pull these two values out of our distribution. Now, the confidence interval for the model. Again, this formula looks very similar to any other confidence interval. It's got an expected value. It has a critical value of t. The last component is a little bit more complicated because we're taking the variance, represented by mean squared error, and multiplying it by the distance value. So we'll walk our way through this formula. First thing we want to look at is the expected value of y. And we're going to do this at a home of 1,300 square feet. Simply plugging in 1,300 square feet into our formula to find the expected value, 64.944. Second, we're going to look for the distance value. 1 over n, 1 over 13. The distance, 1,300 minus 1,203. The distance is 97, and we're going to square that distance. And divide that by 1,667,204 SSXX. That gives us a distance value 0.0826. The critical value of t, again 2.201, driven by alpha and error degrees of freedom. Where do we find mean squared error? It's going to be on the ANOVA table, out of our regression model. Mean squared column, error row, gives us a mean squared error, and that mean squared error of 55.85 is the variance around the model. So we put this all together and we get a margin of error 2.201 times square root of 55.8475 times the distance value 0.0826. That gives us a margin of error 4.727. So our upper confidence limit is going to be 64.944 plus 4.727, 69.67. Lower confidence limit, 64.944 minus 4.727 for 60.217. So for a 1,500 square foot home, we could expect the actual price to be between, or the expected price to be between 69 and 60. The prediction interval, again, is going to give us the range where we might expect to find a single home. The only difference with this formula is we're going to add 1 to the distance value before we multiply that against mean squared error. So the same point estimate, the same distance value, the same critical value of t, the same mean squared error. Only difference, 1 plus distance value. And that's going to give us a margin of error, 17.114. So the upper confidence limit is 82.058. And the lower confidence limit is 47.83. So where could we expect to find an individual home 1,500 square feet? Anywhere between 47 and 82.